Usually a basic part of improving the performance of a program is being able to measure the performance of the program, and a basic tool for doing that in the Wolfram language is the timing function. For example, here's a simple test program that adds the integers 1 through 10 million, and this shows that program enclosed in the timing function, which gives the result of the calculation along with the time and seconds used by the computer. This particular program used a little over 3 seconds on this computer. There are, of course, other ways of doing that calculation. Here's a program that uses the range function to get a list of the integers and then the total function to add up the elements in that list, which gives the same result as before. And the timing function shows that this program is about 100 times faster, finishing the calculation in a few hundredths of a second rather than in a few seconds. Unlike the first program, this second program has to build a list of 10 million integers as an intermediate result, which doesn't take much computer time, but it does take a significant amount of computer memory. The memory used by that list of integers is given by the byte count function, which shows a little over 80 million bytes for the whole list, or about 8 bytes per integer. This Wolfram language session is running on a 64-bit computer where an integer uses 64 bits or 8 bytes of computer memory. An even faster way of adding up the first 10 million integers takes advantage of the fact that there is actually a simple formula for that sum. The formula can be obtained using the sum function. The sum function uses that formula to get the same result without the need to build a list of 10 million integers, and timing shows the calculation finishes many thousands of times faster than the original program with the do loop. The time for doing this calculation using sum has the additional advantage of not depending on the number of integers. The time for using sum to give the sum of the first billion integers, for example, is about the same as the time for summing the first 10 million integers, since all it has to do is substitute a different value into the same formula. The time using range and total, on the other hand, goes up by about a factor of 100, since that calculation involves allocating 100 times as much memory and does 100 times as many additions. For a slightly more realistic example, instead of adding up the first 10 million integers, consider adding up 10 million measurements or 10 million data points, such as the elements in this list of 10 million random integers. Now there's no simple formula for the sum, so the sum function is not as useful. The fastest method of adding up the elements in that list is the total function, which does the calculation in a small fraction of a second. Another interesting method for getting that sum uses the apply function. Applying plus to the list turns the list into a sum, and evaluation of that sum gives the total. This is not a bad solution either, but it is not as fast as using the total function, since the total function has been optimized for the specific purpose of doing this sort of calculation. These first few examples already illustrate several of the most important principles of efficient programming in the Wolfram language. One principle is that built-in functions like range and apply and total and functional programs in general will almost always be faster than programs that are built up using lower-level procedural operations like do loops. Also, when using built-in functions, a special purpose function like total that has been optimized for a particular operation will almost always be faster than a more general purpose function like apply. Procedural loops like do loops can be quite useful and sometimes gives the most natural way of organizing a program, but when there are alternatives, procedural loops typically do not give the fastest programs in a high-level language like the Wolfram language. And finally, when a better algorithm is available, like using the sum function in this example, the better algorithm will almost always be faster. There are many other principles of efficient programming that apply to various common situations that come up in programming. This program, for example, is typical of programs that accumulate a result while the program is running. This program steps through the elements of a list and returns the positions of certain elements, but of interest here is not the details of this program, but how this result is accumulated. This program uses sow and reap to accumulate the result, which is a relatively efficient way of doing this sort of thing. Sow applied to an expression saves that expression internally, and the enclosing reap function collects those expressions and returns those expressions in a list. Another good way of accumulating results is shown by this program, which uses nested lists rather than sow and reap. In this program, expressions are added to the result by adding another level of nesting to a list. The same result as before can be obtained by applying flatten to the nested lists. Finally, here is a third program that accumulates the same result, but this program is not very efficient, especially if the list to be accumulated is large. This program uses the append function to append each new expression to the result. The relative speed of these three methods can be made more apparent by running these programs on larger lists. This generates a sample list with 100,000 elements, and these inputs show the time for running these three programs for this larger list. Since only the time is of interest here, these inputs show only the first element in the result from the timing function. The timing results show that the first two programs use roughly the same amount of time, but the third program is considerably slower. The third program is slower because appending an element to a list requires creating a new list with space for one additional element, copying the elements from the original list into the new list, and inserting the appended element, all of which requires time proportional to the size of the list. And so as the list grows, so does the time needed to append an element. The time for that last program actually grows like the square of the number of elements in the list. For example, if that program is run for a list that is twice as large, say 200,000 elements rather than 100,000 elements, the time increases by a factor of 4. The general principle is to use an efficient method like sow and reap or nested lists for accumulating results. Another principle of efficient programming applies to programs like this one that often need the result from the same calculation many times. This is a rule-based program that gives a recursive definition of Fibonacci numbers, where each number in the sequence is the sum of the previous two numbers. This program gives fast results for small numbers, but the time increases very rapidly for larger numbers. The increase happens because each application of the recursive rule for f generates two additional applications of the rules for f, and the number of evaluations quickly becomes enormous. Many of those calculations, though, involve calculating the same thing. It turns out, for example, that evaluation of f of 31 involves about 120,000 evaluations of f of 6. Those redundant evaluations can be eliminated quite easily in this example by changing the recursive rule so that it adds a new definition for f each time a result is calculated. After that change, calculating results even for fairly large numbers is now quite fast. This speed improvement involves saving or caching lots of new definitions for f. Those new definitions are shown in the display from $f. The addition of all those new definitions does require a small amount of computer memory, and searching through a long list of rules takes time, but in this and many other examples, the speed improvement is more than enough to compensate for the use of memory. The general principle here, which applies dramatically to this recursive program but also applies to other programs, is to avoid unnecessary redundant evaluations by saving results that will be used many times. One broad area of speed improvement applies to programs that work with numbers, which can often be made considerably faster using the compile function and compiled evaluation. To see how compiled evaluation works, here is a simple example of a compiled program that just computes the square of a number. The compile function returns a compiled function expression that can be used much like an ordinary pure function. This input, for example, applies that compiled function expression to a number to get the square of the number. A big difference between compiled evaluation and an ordinary pure function is that every expression that comes up in compiled evaluation must be either a number or a list of numbers, or a Boolean expression or a list of Boolean expressions. Here, for example, is a corresponding program with a pure function that also takes one argument x, and that can be applied to a number to get the square of the number. Comparing those two examples, the compile input includes not only the variable, but also the type of the variable. In this example, the first argument in compile specifies that the variable x is expected to be a real number. If a variable does not have the expected type, such as in this input where the variable is a list of numbers rather than a single real number, compiled evaluation generates an error message and uses uncompiled evaluation to get a result. To better show the performance benefits of compiled evaluation, it is useful to consider a larger example. Here's an example that shows compile used for a relatively slow procedural program with a do loop. This program adds up the elements in a list of numbers. The first argument in compile specifies that the variable x is expected to be a list of real numbers, and the second argument in compile is the actual program. Now generate a list of 10 million random numbers to use for testing this program, and use timing to check the speed of the program. For comparison, this shows timing for evaluation of the corresponding uncompiled evaluation. For this program, compiled evaluation is about 40 times faster than uncompiled evaluation. A functional method, such as using total, is still faster, but compiled evaluation is faster than an uncompiled evaluation that uses the same method. Although compiled evaluation can call uncompiled evaluation, calling uncompiled evaluation from within compiled evaluation does slow down the calculation. Uncompiled evaluation is sometimes useful, such as for getting the values of global variables or calling previously defined functions, but compiled evaluation will speed up the calculation only if most things are handled within compiled evaluation. As an example of that, here's a simple test program that adds the value of a global variable g to itself 20 million times. This calculation finishes in a few seconds. A compiled version of that program can be created by simply using the entire program as the second argument in compile. This program takes no arguments, so the first argument in compile is an empty list. And timing shows that this compiled program is actually slower than the uncompiled evaluation of the same program. The compiled program is slower because compiled evaluation has to use uncompiled evaluation to get the value of the global variable, and all of those uncompiled evaluations result in a slower program. This can be addressed by changing the compiled program to use the value of g as an argument. Now compiled evaluation is much faster than uncompiled evaluation. The general principles for making good use of compiled evaluation are that compiled evaluation will almost always be faster for programs that work with numbers or arrays of numbers, and compiled evaluation also supports Boolean expressions and arrays of Boolean expressions, and compiled evaluation will be faster for programs where at least the most time-consuming parts of the program don't require external evaluations or anything else outside of compiled evaluation. Before closing, there are a few technical details related to timing that are worth noting. One of those details is that the timing function shows only computer CPU time used by the Wolfram language kernel. For example, this evaluation uses several seconds before the result is returned, but timing reports only a fraction of a second, since most of the time is spent not inside the Wolfram language kernel, but in the external processes that get information from the web. In situations like this, there is a different function called absolute timing that gives the total elapsed real time for the evaluation, including time used in external processes. Also, neither timing nor absolute timing give the time needed for formatting a result. For example, this input will generate a list of 10 million integers. After the evaluation is started, it takes several seconds for the display to appear. The result shows that the CPU time for this calculation was a small fraction of a second. Nearly all of the several seconds that it took for the display to appear was spent formatting the result, or in this case, determining that displaying the entire list would exceed a size limit and then working out how to display part of the result, all of which takes a certain amount of time. If the display of the result is not really needed, the display can be suppressed by putting a semicolon after the input. With that change, the calculation returns in a small fraction of a second. Timing can also be dramatically affected by caching of results. For example, this input uses the natural language system to load an image, and after that, a second evaluation of the same input is much faster because the image was saved from the earlier evaluation. There are many examples throughout the system of things like this that are cached automatically, so when a program is faster the second time it's run, it's often because something was cached from an earlier calculation. Finally, for a variety of mostly system-related reasons, the time even for identical calculations can vary from one evaluation to the next. For example, this calculation shows a slightly different amount of time each time it's evaluated. In situations like this, a more accurate estimate of the time can be obtained by doing the calculation over and over several times and averaging, which is done automatically by the repeated timing function. This is mostly an issue for timing things that are relatively fast or when especially accurate timing is needed. That's the end of the examples for this section. In the Wolfram documentation, links to information on functions used to measure time performance of Wolfram language programs can be found in the guide page on time measurement and optimization, and links to information on functions for measuring memory performance can be found in the guide page on memory measurement and optimization. For compiled evaluation, there is a short tutorial following a link in the tech note on evaluation of expressions to the section on compiling Wolfram language expressions, and much more extensive documentation covering a variety of details of compiled evaluation can be found in links from this page on the Wolfram System Compiler.